In this deck, we focus on a real operational failure mode that static appointment systems cannot handle well: uncertainty. In real transportation, trucks do not arrive exactly as planned. Traffic, weather, and mechanical issues push arrivals outside their scheduled windows, which can cause dock overcrowding at the worst times and idle resources at the best times. A dynamic truck appointment system aims to reschedule appointments in real time as new information arrives. The objective is to reduce total system cost, not just truck waiting time. That total includes waiting, labor, and operating cost from opening capacity, and penalty charges when appointments are missed. The system must stay efficient, but it must also stay flexible. The scenario is Harbor View Container Terminal. It processes 2,500 truck appointments per day across 24 operational dock doors. Congestion is concentrated during peak hours from 1000 to 1400, when trucks arrive outside their windows because of delays on the adjacent highway. Off-peak from 2200 to 600, the opposite problem appears. Dock resources are underutilized while labor cost continues. The motivation for dynamic scheduling is to use real-time truck location, weather forecasts, and historical delay patterns to reschedule intelligently. We solve the dynamic appointment problem through a tiered toolkit that moves from principled optimization to scalable real-time control. Tier 1 uses two-stage stochastic programming to model uncertainty with explicit delay scenarios. Tier 2 uses priority-based dynamic scheduling to reschedule quickly as updates arrive. Tier 3 applies particle swarm optimization to explore better schedules under complex trade-offs. Tier 4 uses queue learning to learn rescheduling policies. Tier 5 embeds decisions in an integrated digital twin. Tier 6 moves to autonomous multi-agent scheduling. Tier 7 adds a human and artificial intelligence symbiotic partnership. Tier 10 focuses on proactive demand and market shaping. Tier 1 treats dynamic appointments as a two-stage decision problem. In the first stage, you assign initial appointment slots before uncertainty is realized. In the second stage, after delays occur, you take recourse actions by rescheduling trucks into different slots. Uncertainty is represented by delay scenarios, each with a probability. The objective trades off three cost components: operating cost for the planned schedule, expected waiting cost under each scenario, and rescheduling cost when you change appointments. This structure captures a key reality. Sometimes it is worth paying a rescheduling cost now to prevent a much larger waiting cost later. This slide defines the main sets for the stochastic model. You have a set of time slots, often described as a planning horizon, divided into equal intervals, such as 30-minute blocks. You have a set of trucks requesting appointments. You also have a set of delay scenarios. Operationally, the scenario set is what turns uncertainty into something the model can reason about. Instead of pretending arrival times are fixed, the model considers multiple plausible delay outcomes and chooses a plan that performs well in expectation across them. Parameters describe the uncertain environment and the cost structure. Each scenario has a probability. Each truck has a delay value under each scenario. Each time slot has an operating cost. You also have a waiting cost per unit time and a rescheduling cost per appointment change. These parameters are crucial because they encode the terminal's priorities. If rescheduling is cheap, the system should adapt aggressively. If rescheduling is expensive due to contracts or penalties, the system should adapt more conservatively. The model uses variables for both stages. First stage variables assign each truck to an initial slot. Second stage variables reassign trucks to slots under each scenario. The model also tracks waiting time under each scenario. Operationally, this matters because the same initial schedule can lead to very different queuing outcomes depending on which delays occur. By modeling waiting explicitly, the optimization avoids solutions that look fine only in the no-delay case. This objective includes a deterministic part and an expected part. The deterministic part represents the operating cost of the initial schedule. The expected part represents the probability-weighted sum of waiting cost and rescheduling cost under each scenario. The practical meaning is that the model is not optimizing for one perfect day. It is optimizing for an average day across the distribution of likely delays. That is exactly the logic you want when the terminal faces repeated uncertainty every day. This constraint enforces that each truck receives exactly one initial appointment slot. Operationally, this is a commitment made to the trucker before the day unfolds. Even in a dynamic system, you start with a baseline plan, because carriers need a schedule to target. This constraint enforces capacity limits in each time slot. You cannot schedule more trucks than the slot can handle. Capacity constraints are the main mechanism that prevents dock overcrowding. If capacity is ignored, the system will simply push every truck into the same peak window, and queuing will explode. This constraint links delays and reassignment decisions to waiting time. If a truck is delayed beyond the time it can be served, the difference shows up as waiting unless reassignment moves it to a later slot that aligns with its actual arrival. Operationally, waiting time is where customer pain appears, drivers idling, missed downstream commitments, and congestion that spills into surrounding roads. This constraint ensures that under each scenario, the combination of the initial assignment and any reassignment results in exactly one effective slot for each truck. Operationally, this prevents contradictory plans. A truck cannot be both kept in its old slot and moved to a new slot under the same scenario. The system must choose one executable instruction. This slide enforces variable domains. Assignment variables are binary and waiting time is non-negative. Operationally, this keeps the model grounded. A truck cannot be assigned half to a slot, and waiting time cannot be negative. This slide visualizes the stochastic programming network flow for dynamic appointments. The network view helps you see two-stage structure as a flow through time. Initial assignment decisions feed into scenario-specific paths, and those paths include adjustments that represent rescheduling. It makes uncertainty tangible by showing how one plan branches into multiple outcomes. This example uses 3 trucks and 3 time slots under 3 delay scenarios. The probabilities are no delay with probability 0.4, light delay with probability 0.4, and heavy delay with probability 0.2. The costs are operating cost 100 per slot, waiting cost 5 per minute, and rescheduling cost 50. The stochastic model's expected total cost is 421 compared to 580 under static scheduling. The lesson is that planning for uncertainty plus allowing recourse can reduce expected cost significantly. Tier 2 is built for real time. It maintains a priority queue of trucks and updates priorities as new delay information arrives. The priority score blends expected delay, urgency, and cost impact, so the system reschedules the trucks that create the largest expected disruption first. The key operational benefit is speed. The method can run each time new data arrives, rather than solving a full stochastic model from scratch. This flow diagram shows the loop. Receive real-time updates, compute or update priorities, check slot availability, reschedule if beneficial, and publish the updated appointment plan. Think of this as a control cycle. The system is continuously steering the appointment plan toward feasibility and efficiency as conditions change. In the first code section, you typically see the data structures for appointments, slot capacities, and a priority queue keyed by a composite score. Operationally, priority recalculation is the key detail. If delay predictions change, the queue order must change. Otherwise, the system reacts to outdated information and will reschedule the wrong trucks. This section typically contains the rescheduling logic. Pop the highest priority truck, search for feasible alternative slots, estimate the benefit of moving, and commit changes when the improvement justifies the disruption. The practical trade-off is stability versus responsiveness. Too much rescheduling creates chaos for carriers. Too little rescheduling allows congestion to build. The heuristic must balance those pressures. This slide gives a concrete update cycle with 5 trucks scheduled from 900 to 1200. At 8:30, the system receives delay estimates and priorities. Truck C has a 45-minute delay with priority 120. Truck A has a 30-minute delay with priority 85. Rescheduling reduces total waiting time from 140 minutes to 65 minutes. The key point is that the system attacks the largest disruptions first and converts them into manageable shifts. Tier 3 uses particle swarm optimization. Each schedule is represented as a particle position in solution space, and velocities represent how assignments change across iterations. The fitness combines waiting, operating, and rescheduling cost components. Swarm communication lets particles learn from their own best solutions and the best solution found by the group, which helps explore trade-offs and converge to lower-cost schedules without exhaustively enumerating all possibilities. This slide defines the fitness idea. A schedule is scored by a weighted combination of waiting cost, operating cost, and rescheduling cost. Operationally, the weights encode policy. If the terminal is under pressure to avoid missed appointments, it may accept more rescheduling. If carriers require stability, the rescheduling term should be heavier. This visualization illustrates particle swarm optimization dynamics for dynamic appointment scheduling. Use it to understand the search behavior. Particles move through the space of schedules, pulled toward their personal best and the swarm's global best, while still maintaining some randomness that helps avoid stagnation. In the first pseudocode part, you usually initialize a swarm of particles, assign random schedules, and evaluate initial fitness. Operationally, initialization matters because it controls exploration. Seeding some particles with heuristic schedules can improve convergence speed compared to starting entirely random. This section typically updates velocity and position. That means it updates how schedule assignments shift from one iteration to the next. The core idea is memory plus social learning. Each particle remembers what worked for it, and it also learns from what worked best overall. This is useful when many schedules are feasible, but only a few balance costs well. This part usually includes feasibility handling and stopping criteria. If a particle proposes a schedule that violates capacity or other hard constraints, the algorithm must repair it or penalize it. Operationally, feasibility is non-negotiable. A schedule that looks cheap but isn't feasible will fail in live operations, so the optimization must enforce feasibility consistently. This slide reports an example run, 8 trucks and 6 time slots, with 30 particles over 500 iterations. Fitness improves from 2,450 to 1,180, a 52% cost reduction. The operational interpretation is that shifting a small number of trucks out of peak pressure can produce a large system benefit when waiting time is expensive. Tier 4 uses reinforcement learning, specifically queue learning, to learn an appointment management policy through interaction with a simulated environment. Actions include maintaining the schedule, rescheduling a truck to another slot, offering incentives for voluntary changes, or adjusting capacity temporarily. The reward penalizes waiting, operating cost, and rescheduling penalties while rewarding service quality. Over time, the agent learns which interventions prevent congestion with minimal disruption. This slide defines the state as the current appointments, truck locations, delay predictions, and slot utilization. Operationally, this is what the decision maker needs to know to act. Without location and delay predictions, the system is blind. Without utilization, it cannot anticipate bottlenecks. This slide defines the reward structure as a weighted balance of waiting time, operating cost, rescheduling penalty, and service quality. The key insight is that reward design is policy design. If you penalize rescheduling too strongly, the agent will avoid needed adjustments, and queues will grow. If you penalize waiting too weakly, the agent will tolerate long queues and harm service. This figure shows the queue learning framework for dynamic appointment management. It highlights the feedback loop. Observe the current state, choose an action, observe the cost and service outcome, and update the learned value estimates. Over many episodes, the policy improves. In the first part of the pseudocode, you typically define the environment representation, initialize the queue table or value function approximation, and set exploration behavior. Operationally, exploration must be controlled. The agent must try alternative actions to learn, but in a real deployment, you would constrain exploration to safe actions and learn primarily in simulation. This part usually contains the action selection step and the update rule that blends immediate reward with the best estimated future value. Operationally, the update rule is what turns experience into policy. If the system repeatedly sees that rescheduling early prevents later queues, the learned values will favor that action in similar future states. This section typically continues the training loop across episodes, including state transitions, reward computation, and tracking performance metrics. Think of training as repeated practice days. The agent experiences many synthetic days of operations with delays and learns how to keep the dock stable. This final pseudocode part often includes policy extraction and evaluation against baselines. Operationally, evaluation is the quality gate. The learned policy must be compared to static scheduling and simple heuristics to confirm it is actually improving cost and service. This slide reports outcomes after training for 10,000 episodes. The agent proactively reschedules predicted delays above 30 minutes and maintains 85% utilization during peak hours. Average waiting time drops from 45 minutes to 18 minutes, with 23% cost savings compared to static scheduling. A key behavioral insight is that offering incentives of $25 is more effective than forced penalties of $75. Tier 5 uses a digital twin, a synchronized virtual replica of terminal operations connected to real data. The twin continuously recalculates optimal schedules and runs what-if scenarios. It integrates GPS, RFID, weather forecasts, traffic systems, and crane schedules. The operational value is anticipation. You do not wait for congestion to appear, you predict it and prevent it. This slide shows the digital twin system architecture for terminal operations. Use it to understand integration. A dynamic appointment system is only as good as its data. The architecture makes clear how sensing, prediction, simulation, and optimization connect into one control loop. This slide provides a concrete disruption example. The twin processes 2.3 million data points per hour from 180 trucks, 12 cranes, and 48 dock positions. It runs 1,000 scenario simulations and predicts disruption for 18 to 22 hours starting at 14:30. It preemptively reschedules 340 appointments and reduces storm-related delays by 67%, saving about $2.3 million. The lesson is that proactive rescheduling beats reactive firefighting. Tier 6 moves to distributed intelligence. Truck agents and terminal resource agents negotiate appointment slots rather than relying on one centralized scheduler. Truck agents bid based on constraints and priorities, and terminal resources adjust pricing and availability dynamically. This can reduce single points of failure and enable emergent load balancing when disruptions occur. This slide shows the multi-agent system architecture for autonomous scheduling. Operationally, architecture matters because negotiation needs coordination infrastructure. You need communication channels, bidding rules, and a way to resolve conflicts when multiple agents compete for the same capacity. This slide reports emergent behavior metrics. A dock door failure triggers redistribution of 47 appointments in 12 minutes, maintaining 94% throughput. Appointment adherence improves from 76% to 94%. Truck waiting time decreases by 43%. Terminal utilization increases by 18% without adding infrastructure. The key point is that distributed systems can recover quickly when local disruptions occur. Tier 7 formalizes human oversight. The system provides explainable recommendations, and humans apply judgment in cases where customer relationships, exceptional cargo, or strategic priorities matter. The system learns from human overrides to improve future recommendations. This creates a collaboration where artificial intelligence handles the routine high-frequency optimization, while humans manage exceptions and ensure the plan aligns with business goals. This slide shows the human and artificial intelligence collaborative framework for schedule optimization. Use it to understand roles. The system provides confidence, alternatives, and risk assessments. Humans approve critical changes and provide context the model cannot quantify. This slide reports that human overrides occur in 8% of cases. Those interventions improve customer satisfaction by 15% and generate additional revenue of $1.2 million over 6 months due to service quality and loyalty. The operational message is that a small amount of human intervention can create outsized business value. Tier 10 moves from reacting to demand to shaping demand. The appointment system uses dynamic pricing, incentives, and behavioral nudges to move customers into off-peak slots. The goal is to reduce peak concentration while improving satisfaction and profitability. Instead of fighting congestion every day, the system changes the pattern that creates congestion. This slide presents the proactive market-shaping architecture. It links forecasting, pricing, incentives, and customer communication into a single mechanism design loop. Operationally, you are not only scheduling trucks, you are influencing choice. This slide reports results over 18 months. Peak concentration from 1000 to 1400 drops from 67% to 34%. Average appointment costs decrease by 12%. Terminal throughput increases by 28%. Customer satisfaction rises from 7.2 to 8.9 out of 10. Annual savings are 4.7 million euros. The key lesson is that shaping demand can unlock capacity without building new infrastructure. This slide lists market intelligence insights. Delay prediction is accurate 48 hours ahead with 84% accuracy. Personalized recommendations make customers 340% more likely to choose off-peak slots. Small incentives of 25 to 40 euros outperform penalties above 100 euros. Operationally, incentives and messaging can be cheaper and more effective than punishment. These practice questions reinforce the first two tiers. Tier 1 asks you to formulate a stochastic model with 4 slots and 6 trucks, each with a 30% probability of a 20-minute delay, using operating cost 150 per slot, waiting cost 8 per minute, and rescheduling cost 75. Tier 2 asks you to run a priority update sequence for delayed trucks and quantify improvement versus static scheduling. The learning goal is to connect the model logic to the real-time heuristic behavior.